Okay, so last time we were talking about the butcher tableau. And this is a way of compactly representing the coefficients or the parameters. It's like of a Runge-Kutta method. So it's oftentimes denoted by a C B transpose. And then again, in terms of components, it'll be A11 to A1S, AS1 to ASS, and then C1 to CS, and B1 to BS. Okay, so it's conventional when writing down the butcher tableau to omit the trailing zeros. It's like on this A matrix. Okay, so it's conventional to omit the trailing zeros in each row of the butcher tableau. Okay. So some things you can immediately see, it's like from just the form of the butcher tableau, is that if all the non-zero entries of the matrix A are below the diagonal, and what that immediately tells you is that the method is explicit. Okay. Otherwise, the method is implicit. So it should be noted, of course, that if you have an implicit Runge-Kutta method, then one of the things that's like which we saw before is that instead of trying to solve the system of equations using something like the Newton method, you could potentially apply a fixed point iteration, right? So you could attempt to solve a system of equations using fixed point iterations. Okay, and oftentimes that's desirable because in contrast to Newton, you don't have to form the Jacobian, and computing the Jacobian of a large number of systems of nonlinear equations in multiple variables is going to be very, very expensive. So it's best to avoid having to compute it, the Jacobian, for example. So let's now look at a simple example of an implicit Runge-Kutta method. And it may not be immediately obvious as stated that it is a Runge-Kutta method. But let's just try to consider one and then to rewrite it in a form where it's sort of apparent that it is a Runge-Kutta method. So that's what is called the implicit midpoint rule. And you can think of the implicit midpoint rule as arising when you apply the midpoint quadrature formula to the fundamental theorem of calculus. Right? So it has the form that yn plus 1 is equal to yn plus hf evaluated at the midpoint of the previous and the current solution. So that's yn plus 1 over 2. Okay. All right. So that's not immediately. It's like of the form of a Runge-Kutta method. But if you look at this, what you'll see is that you have the solution in new time, solution in old time, plus some weighted combination of the vector fields at a bunch of points. Okay, so you should think of, when you look at something like this, you should think of this yn plus 1 over 2 as being one of these internal stages. So let's call that y1. Okay, so capital Y1. Okay, so let's try to then write everything down. So what this identification allows you to do, it allows you to say that yn plus 1 is equal to yn plus h f evaluated at y1. So this equation then, it has the form it's like you want for a Runge-Kutta method, but you still have to have an expression for what y1 is. Okay, so y1, you can check it's like satisfies the following equation. Okay, so y1 is equal to yn plus h f evaluated at y1. Okay, so where do you see this coming from? Okay, so let's try to see it's like where you could derive that. So you know that y1 is equal to yn plus 1 over 2. Okay, and you know what yn plus 1 is. And okay, so this is yn over 2 plus okay, 1/2 yn plus hf at y1 by definition. Okay, so this is of course nothing more than yn plus 1. Okay, so let's put this together. This is yn plus h over 2 f evaluated at y1. Okay, so I think I've messed up. Yeah, there's 1/2 here. Okay, so now it's like you're in the form which you want. Okay, that you have an internal stage equation. Y1 is equal to yn plus h over 2 f at y1, and you have yn plus 1 is equal to yn plus hf evaluated at y1. Okay, so let's try to compare this to the general form of a Runge-Kutta method. So the general form of the Runge-Kutta method is that the internal stage yj is equal to yn plus h sum of a ij f evaluated at yj, and yn plus 1 is equal to yn plus h sum over bi f evaluated at yi. Okay, so now it's like you're in business. You can see that just comparing this equation with this equation, that you know, it's like, well, I goes from 1 to s. There's only one stage, which is the s equals to 1. So you know that s is equal to 1. So there's one quadrature weight. So that tells you that b1, so what is b1? b1 is going to be 1/2. Okay. And then there is another quadrature weight for the a11 term. Okay, so there's an a11 term. And I'm sorry, no, b1 is equal to 1, right? Because I'm looking at this equation. So b1 corresponds to this equation. The a11 corresponds to the first equation here, and that has a weight 1/2. Okay, so the only thing it's like which is missing is c1. Okay, so c1 you should think of as being the time at which is associated with the first stage equation. Okay, so so if you look at this, it's you have a midpoint of this, and you should imagine that this y1 is an approximation, if you will, of y at tn plus h over 2, right, which is sort of the midpoint between time tn and tn plus 1. So that's telling you that c1 is 1/2 as well. Okay, so now you're ready to put everything together into the form of a butcher tableau. And again, as a reminder, a butcher tableau looks like a matrix A with a vector C and a row vector B transpose. Okay, so let's try to put this butcher tableau together. So you have the A matrix. Since S equals to 1, it's like things are relatively simple because then you just have a 1 by 1 matrix for A. The A matrix is just 1/2. You have the C corresponding to the time, if you will. It's like at which the first stage corresponds to. That is again 1/2. And then you have the quadrature weight, B, okay, B1, which is 1. So the bottom line then is that for the implicit midpoint rule, it corresponds to the following Butcher tableau. All right. So let's look at a few other examples of Runge-Kutta methods and their corresponding Butcher tableaus. So you have the, so let's look at examples. So the simplest example, of course, is the Euler method. Right, so Euler method just says yn plus 1 is equal to yn plus h f evaluated at yn. Okay, so you know that this is the equation. It's like which tells you what the update is. So you should compare this to yn plus 1 is equal to yn plus h times the sum I equals to 1 to s of bi f evaluated at yi, which is the internal stage. So by comparing these two, it's like some things are readily apparent. The first of which is that there's only one stage, s is equal to 1. Okay, the second thing it's like you can conclude from this is that b1 is just 1. And the third thing you can conclude from this is that y1 is just yn. Okay, so with these identifications in mind, you can rewrite the Euler method in the following way: y1 is equal to yn, and yn plus 1 is equal to yn plus h f evaluated at y1. Okay. So you have this thing here, okay, saying that the first stage just corresponds to being yn. So that tells you that the time at which this corresponds to is just tn plus 0 times h. So this means that c1 is equal to 0. Okay. And it also tells you that because there are no terms added onto it, it also tells you that a11 is equal to 0. So the Butcher tableau for the Euler method then just looks like the following. So there's a 0 here corresponding to the a11 term. There's a 0 here corresponding to the c1 term. And then there's a 1 corresponding to the b1 term. Okay. So that's the Butcher tableau for the Euler method. So let's look at another example, which is the trapezoidal rule. Okay, so that says that yn plus 1 is equal to yn plus h over 2. I'm going to expand this out. F evaluated at yn plus h over 2 f evaluated at yn plus 1. Okay. All right. Again, it's like if you want to compare it with the form of a Runge-Kutta method, then this immediately suggests to you that you should think of yn as being big Y of 1, the first stage, and yn plus 1 as being y2. Okay. So I need to write down, it's like an equation for y1, y2, and yn plus 1 as yn plus h over 2 f evaluated at y1 plus h over 2 f evaluated at y2. Okay, this last equation immediately tells you that b1 is equal to 1/2 and b2 is equal to 1/2. Okay, all right, so now let's write down the expressions for y1 and y2. So y1 from this is just nothing more than yn. Okay, so this tells you that a11 is equal to 0, a12 is equal to 0. And you can also conclude that c1 is equal to 0 here. And y2 is yn plus 1. Okay, so this is associated with the final time, so this means that c2 is equal to 1. Okay, but let's write down what yn plus 1 is. Okay, so yn plus 1 is again yn plus h over 2 f evaluated at y1 plus h over 2 f evaluated at y2. Okay, so this tells you, okay, so these tell you that a21 is equal to 1/2 and a22 is equal to 1/2. So now you can put this all together to give you the following tableau. Okay, a11 is 0, a12 is 0, a21 is 1/2, a22 is 1/2. Okay, c1 is 0, c2 is 1, b1 is 1/2, and b2 is 1/2. So this gives me then again the butcher tableau for the trapezoidal rule. Okay. All right. So now I'm going to give you another example of a Runge-Kutta method expressed and write this in terms of a butcher tableau. So this is the fourth order Runge-Kutta method, explicit Runge-Kutta method. It's not necessarily the best method. It's like in any sense, it's like, but it is nevertheless very commonly used, and the main reason is that it's easy to implement and it's explicit. So it has the following form: y1, the first stage, is just the initial value. The second stage involves basically a half Euler step. Okay, so yn plus 1/2 of h. It's like evaluated with the vector field evaluated at the initial value. Okay, and the third stage also involves a half Euler step, but using the vector field from y2, sorry. Okay, so this is y2, h over 2, f evaluated at y2. And then the fourth stage, y4, is a full step of the vector field, which evaluated at the point y3. Okay, and then the final update that involves some linear combination of these. So yn plus 1 is equal to yn plus h. Let's see, so this is 1/6 f evaluated at y1, 1/3 f evaluated at y2, 1/3 f evaluated at y3, and 1/6 f evaluated at y4. Okay, so hopefully by now it's like you should be fairly comfortable with reading off the coefficients of the Runge-Kutta method. So if you look at this, this has an approximation. Essentially, it's like at the time tn. So c0 here is just going to be 0, and then, no, let me just put this as c1. Okay, and then c2 is going to be 1/2, c3 is going to be 1/2, and then c4 is 1. Okay, and then from these, it's like you can start putting together the coefficients, the Aij coefficients. So you know here that a11 equals to a12 equals to a13 equals to a14 equals to 0, right? So here the only non-zero coefficient is the a21 term. Okay, so a21 is going to be 1/2, but a22, a23, and a24 are going to be 0. From here, the first non-zero coefficient is a 2, 3, which is again 1/2, and then the other terms, a 3, 2 is 1/2, and then a 3, 1 is a 3, 3 is a 3, 4 is 0. Okay, and then here the non-zero entry is a 4, 3, which is 1, and then a 4, 1, a 4, 2, and a 4, 4, 0. Okay, and then from this equation you can read that B1 and B4 are 1, 6, and B2 and B3 are 1/3. Okay, so now you can put all this together, again in the form of a butcher tableau. Okay, so you have 0, 0, 0, 0, 1/2, 0, 0, 0, 0, 1/2, 0, 0, 0, 0, 1, 0. Okay, and then the C entries, 0, 1/2, 1/2, 1, and then the B entries, 1, 6, 1/3, 1/3, and 1, 6. Okay, so there are some things it's like you can start observing, if you will. Okay, so as we saw before, this butcher tableau has a matrix which is strictly lower triangular, and you know that implies that the method is explicit. And if you look at how the formulas are written, it's fairly clear to you, should be fairly clear, that this is something which you could implement as stated in a way which doesn't require you to solve any nonlinear equations. The right-hand sides only invoke things which you know from the previous equations. Okay, so it's consistent with what we know, that the structure of the A matrix, if it's strictly lower triangular, corresponds to an explicit method. So the other thing which you'll see, it's like as we go along, is that the C coefficients, if you will, correspond to the corresponding row sum. Okay, so if you sum up the entries in each row, you'll see that they correspond to the C values. And the same is true implicitly of the very last row. Okay, so the very last row has to sum up to 1. And we'll see later that this is a consistency condition. If you don't have that, then basically the Runge-Kutta method could not even exactly compute the solution for a constant vector field. Okay, so that's the form of this 4th-order explicit Runge-Kutta method, extremely commonly used, not necessarily the best method out there, but nevertheless it's useful to know that it exists.